Good morning, everybody. So today we are going to start with a new concept or new topic. Is called matrix. It is a very important topic. It has a lot of practical usage. Many of the things that you use in your everyday life or you're excited about, behind the scene, it's using matrix. Like for instance, nowadays, you hear about self-driving cars, okay? In particular, everybody knows about Tesla around here, right? Or pretty much globally, many people know about Tesla, right? The technology that goes behind a self-driving car, Tesla, or any other self-driving car, like Google has one too, it uses something called machine learning or artificial intelligence. And at the heart of artificial intelligence is this matrix multiplications, okay? Matrix operations. A lot of application of matrices. So it's important to understand what matrices are. The great thing about this is that this topic is really easy. It's not hard, okay? The topics that I'm gonna cover in this class are really, really easy. And it should be very easy to grasp. However, if you have any questions, please do feel free to let me know. Okay, what is a matrix? A matrix is a rectangular array of numbers. Rectangular array of numbers. Okay, rectangular, and also I'd use the word tabular, like a table, right? Rectangular / tabular array of numbers. What is a matrix? It is a rectangular or tabular array of numbers. Now, remember, it doesn't necessarily have to be numbers. Since we are talking about mathematics, it could be a rectangular or tabular array of, I would say, let's say, mathematical objects. Mathematical objects. Okay. Rectangular or tabular array of numbers or mathematical objects. But in this course, we are going to pretty much exclusively be dealing with numbers, but it could be some other things, mathematical objects such as functions. It could be a functions, okay? Or it could be something we call operators. Operator is something that operates on something, okay? Something else. So it could be functions, operators, or pretty much any mathematical objects that make sense. So matrix is more like an abstract idea. It's a rectangular array of items or things, okay? It's a rectangular array of items or things. Now those items could be numbers, it could be functions, it could be operators, it could be sets, or whatever way you define it, all right? Now, matrix is typically denoted by this. Let's say we call a matrix M. So here is a simple example of matrix. 1, 2, 3, 4, 5, 6. That's a matrix. Okay. And this matrix has how many rows? It has 1 row, 2 rows. How many columns does it have? 1 column, 2 columns, 3 columns. So this matrix has 2 rows and 3 columns. So typically we'll denote a matrix this way. M2 by 3. Inside the parenthesis, X, M, open parenthesis, 2 times 3. Okay, it's read 2 by 3. 2 by 3. Don't multiply it. Okay, 2 times 3 is 6. It's written M2 by 3. That tells you we are dealing with a matrix of size 2 by 3. That means it has 2 rows and 3 columns. In general, if you have a matrix A, it has number of rows M and number of columns n, then we would write a m by n, which means that it's a matrix that has m rows and n columns. It's a matrix that has m rows and n columns. Okay. Now, so let's say we have a matrix A. One, 0, -5, 3, 7, 8. A is a 2 by 3 matrix, right? A is a 2 by 3 matrix. Now, individual entries or individual elements of the matrix is denoted by Aij. Aij. So for matrix A, element in the ith row and jth column is denoted by Aij. So for instance, this top left element is in row number 1, and column number 1. It's at the intersection of row number 1 and column number 1. So I denote it by A11, which is 1 in this case. This one is located at the intersection of row number 1 and column number 2. So this should be A12, which is 0. This one is located at the intersection of row number 1 and column number 3. So that would be A13, which is equal to -5. Similarly, this 3 is located at the intersection of row number 2 and column number 1. So I'd write A21 is equal to 3. And this one is at row number 2, column number 2. So A22 is 7. Then the last number 8 is located at row number 2 and column number 3. So we denote it by A sub 23. It's a subscript, by the way. A sub 23 is equal to 8. Row number 2, column number 3. Okay, so that's what it is. All right. Now let's go ahead and do some other things with matrices. There are two special type of matrices. It's called row matrix and column matrix. Row matrix which is just a single row, something like this. -7 to -3. It has only one row, but it has 3 columns. So if you have a matrix that is just a row, we call it row matrix. As you will see in the future, these row matrices become important, or column matrices become important. Now, column matrix, similarly, it just has a column. Okay, so this is, by the way, let's call it matrix A. So this A is, by the way, 1 by 3 matrix. Okay, it's a row matrix. On the other hand, there is something called column matrix. As you can probably guess, it is just going to be a single column, like -5, -2, 0. It is just a single column. Okay, and this matrix, let's call it B, matrix B. It has how many rows? 3 rows, and it has 1 column. In general, a row matrix has this structure. So let's call it a row matrix A. It's going to have 1 row and some number of columns, M. Oh, actually, let's use N. 1 row and some number of columns, N. And a column matrix, let's call it B, it will have M rows and 1 column. So these are the characteristics. A row matrix has one row, but as many columns as you want. A column matrix has one column, but as many rows as you want. So let's see. This is a row, even though it's just one item. This is a row, and this is a row, but this is just a column. Similarly, this is a column, this is a column, and this is a column, and this is just a row. The structure of row matrix is A. Oops, I switched to comma. Let's stick to. Sometimes I think this convention A m by n, or I wonder sometimes some authors use A m by n. That's just a notation saying that it is an m by n matrix, but from the context of the discussion, it will be clear. So A1 by n or A m by 1 matrix. Okay. So this is about row matrix and column matrix. Now, any question, anybody so far about materials? Anyone has any question about so far what we have talked about? All right. If no questions, then I'm going to move on to the next topic involving matrix. It's called matrix operations. Okay. So there are some matrix operations that are defined. Okay. Now, from your experience with arithmetic or algebra, you know there are 4 types of operations that you can perform. Like on the number system, the numbers that you have, you can perform 4 different types of operations. One is addition, right? Another is subtraction. Another is multiplication. Another is division. So these are the 4 different types of operations that you are familiar with, okay? Now, for matrix, by the way, for matrices, by the way, plural of matrix is matrices. So for matrices, this is defined. That means you can add 2 matrices. This is defined, meaning you can subtract one matrix from another matrix. This is defined, means you can multiply 2 matrices, but not always. So this is also here, I need to clarify things. You can add 2 matrices under certain circumstances. You can subtract 2 matrices under certain circumstances. You can multiply 2 matrices under certain circumstances. However, you can never divide 2 matrices. Okay? You can never divide 2 matrices. So let me just clarify it. Matrix division, matrix division is not defined. Okay. Even though I use this division notation, I don't think it applies. We ever use this notation in the context of matrix. I just wanted to save some writing. So matrix division is not defined. Now, addition, I said, yes, you can add 2 matrices, but when? So let's say I give you 2 matrices, okay? 1, 2, 3, 4. B is another matrix, -1, 0, 2, -1. If I were to ask you to add two matrices, it probably would make sense for you to think, okay, so think of it this way. Let's say in the world, nobody knows about matrices. You are the first person exploring it, okay? You happen to be the first person exploring these matrices. You are coming up with a new innovative idea. So how do you define it? Given that you know about addition, subtraction, multiplication, and division, you'd probably say, oh, okay, I'd add this one with this one. I'd add this one with this one. I'd add this one with this one. Add this one with this one. Meaning, I'm going to add the corresponding elements in both the matrices. So positive 1 and negative 1, that's going to give me 0. If I add 1 to negative 1, that's going to give me 0. If I add 2 to 0, that's going to give me 2. If I add 3 and 2, that's going to give me 5. If I add 4 and negative 1, that's going to give me 3. So there you go. This is your addition of two matrices. Okay. If two matrices have the same dimensions, you can add them or subtract them. Now, what if I were to give you this example? Then you'd be saying, it doesn't make sense. If I give you A is equal to 1, 2, 3, 4, and B is equal to 1, 2, 3, 4, 5, 6. Adding these two matrices probably doesn't make sense because this is a 2 by 2 matrix, okay? This is a 2 by 3 matrix. Their dimensions are not the same. These two matrices, they do not have the same dimension. If they don't have the same dimension, you cannot add them or subtract them. If two matrices do not have the same dimension, you cannot add them or subtract them. So you can consider another 2 by 2 matrix. You could add that one with this, or you could consider another 2 by 3 matrix, and you could add that with this matrix. So two matrices could be added or subtracted only if they have the same dimensions. So now let me give you another example of subtraction. So this is something you may want to pay closer attention to because at times I have seen students make mistakes. Okay, so let's see. 2, negative 3, 1, 4, 1, 0. This is my matrix A, and my matrix B is going to be negative 3, 1, negative 2, 4, negative 4, negative 5. Okay, I have these two matrices. You could obviously add these two because they both have the same dimension, 2 by 3. This is, and this is 2 by 3 as well. So you could add them. However, how do you do the subtraction between two matrices, A minus B? How do you do the subtraction? It's pretty much the same thing. You do element-wise addition or subtraction. You do element-wise addition and subtraction. So here is what you do. So 2 minus 3. So I'm gonna do it here. 2 minus 3. Don't do that. That's a mistake. What you are doing, you are subtracting negative 3 when you're doing A minus B. You're subtracting negative 3 from 2. So it's gonna be 2 minus negative 3. So that's gonna give you 2 plus 3. That is gonna be 5. So your first element is gonna be 5. The second number is 3, negative 3 minus 1. So negative 3 minus 1 is going to be negative 4. Negative 3 minus 1 is negative 4. The next one is going to be this one, 1 minus -2. 1 minus -2, there's going to be 1 plus 2 is equal to 3. This is going to be 3. In exactly the same way, you do the second row. 4 minus 4 is 0. So this is going to be 0. 1 minus -4. 1 minus -4 is going to be 1 plus 4, which is 5. So there's going to be 5. And the last one, 0 minus -5. Yes. 0 minus -5 is 0 plus negative times negative is positive, right? 5, which is 5. So this is your A minus B. I gave you this example to ensure that you are comfortable taking into consideration the negative sign, okay, with numbers. Because if you're subtracting, sometimes it's easy to forget the negative sign. So you just need to make sure that you have the negative sign there, okay? So 2 negatives is going to make it positive. So that's how you do matrix subtraction. Now, matrix multiplication, it's a different type of operation that you may have not ever seen before, okay? And of course, matrix division is not defined, so you can just ignore that. So matrix multiplication, excuse me, matrix multiplication. This is probably the most important operation that we do with matrices. The multiplication and multiplication of 2 matrices is very useful, very, very useful. Now, what I'm going to do, I'm not going to talk about multiplication yet, because if I do, then you might be a little bit overwhelmed at the moment. But I will do plenty of matrix multiplication shortly, maybe as early as later in the class or in the next class. The reason I'm kind of postponing it is that it's a bit unusual type of operation. I will have to admit, when I was learning matrix multiplication many years ago, for the first time, I was like, it doesn't make sense. It's kind of strange. It's not something that I'm used to. So if you've got that kind of feeling, that's okay, okay? If you've got some strange feeling about multiplication of 2 matrices, that's perfectly fine. So don't feel anything unusual. Just know that this is a very useful operation, matrix multiplication, being able to multiply 2 matrices. It has many, many, many real-world, meaningful real-world applications. So it's important for you to be very comfortable with matrix multiplication. However, I will talk about some other features of matrices, okay? And then I'm gonna come back and do the multiplication. And always remember, matrix division is not defined. So to summarize, you can do addition, subtraction, and multiplication on matrices. However, under certain conditions, for addition and subtraction, both the matrices that you are adding or subtracting, they must be of the same dimensions. That means they must have the same number of rows and same number of columns. They must have the same number of rows and same number of columns. Okay, but for multiplication, there is a sort of like different rule. The matrices do not have to be of the same dimension. As a matter of fact, it's defined in such a way they are supposed to have different dimensions pretty much most of the time. Okay, most of the times they are supposed to have different dimensions, but at times there could be situations where you multiply 2 matrices, they have the same dimensions. Okay, so let's go ahead and define some other very simple stuff with matrices. Square matrix. Okay. Square matrix. What is a square matrix? A square matrix A is just n by n. That means it has the same number of rows as the number of columns. Okay, the number of rows and the columns are the same. So in essence, in theory, you could have a 1 by 1 matrix. That's a square matrix. You could have 2 by 2 square matrices. You could have 3 by 3 square matrices, 4 by 4 square matrices, and in general, n by n square matrices. Okay, a square matrix is a matrix that has the same number of rows as the number of columns. Same number of rows and columns. So simple example is a 2 by 2 square matrix. -7, 0, 9, -7. It's a 2 by 2 square matrix. 3 by 3 is going to be 1, 0, -1, 0, 2, -2, 3, 0, -1. That's an example of a 3 by 3 square matrix. Now you can go ahead and do 4 by 4 or whatever. In general, n by n. So what is a square matrix? A matrix that has the same number of rows and columns. A matrix that has the same number of rows and columns. Now, next, I'm going to define something called identity matrix. Identity matrix. What is an identity matrix? An identity matrix is a square matrix. A square matrix. Now that you know what is a square matrix, you know what I'm talking about, right? A matrix that has the same number of rows and columns. Identity matrix is a square matrix with ones, okay, along the principal diagonal. And zeros everywhere else. It has ones along the principal diagonal and zeros everywhere else. Actually, it's easier to show an example than writing it out. I'll just give you some examples. What is a principal diagonal? You must know. Is the diagonal that starts from the top left and goes to the bottom right. This is the principal diagonal. And you could have another diagonal like this, right? That's not the principal. That's called, I don't know, secondary diagonal or not principal diagonal. So mainly, we never use the other diagonal. Most of the times, we use the principal diagonal. So principal diagonal is the diagonal that goes from the top left to the bottom right corner. So an identity matrix, 2 by 2 identity matrix, 2 by 2 identity matrix, okay? 2 by 2 identity matrix is 1, 0, 0, 1. It has ones along the diagonals and 0 everywhere else. A 3 by 3 matrix, identity matrix would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. That's a 3 by 3 identity matrix. Okay, it's a 3 by 3 identity matrix. Is this clear, everybody? What is an identity matrix? In general, you could have an n by n identity matrix. They'll have ones along the diagonal, 1 0 0 0 0 1 0 0 0 0 0 1 0, and you keep coming down 0 0 0 0. Last one, oops, let me just, the very last item is, or element is 1. So along the diagonal, principal diagonal, you have ones. So this is the definition of identity matrix. So we talked about two special types of matrices. One is a square matrix and another is identity matrix. A square matrix is a matrix of same number of rows and columns. It has the same number of rows and columns. And identity matrix is a special type of square matrix that has ones along the diagonal, principal diagonal, and 0 everywhere else. Identity matrix has ones along the principal diagonal and zeros everywhere else. And here are some examples of identity matrices. Any question, anybody? No questions? Okay. Everybody okay? All right. All right. So what I'm gonna do right now, I'm gonna talk about some basic properties, okay, of matrices, but I'm gonna introduce the concept by giving you some examples that you are very familiar with. If I tell you 2 plus 3, which is equal to 3 plus 2, right? Both of them are equal to 5, right? For our numbers from the number line, 2 plus 3 is the same as 3 plus 2. This property is called commutative property. This property is called commutative property. What it means is that you can commute the addition process. That means you can switch them around. So in general, we could say a commutative property is A plus B is equal to B plus A, the same thing. So this works, checks. However, this example, it doesn't check. If I say 2 minus 3, 3 minus 2, are they equal? The question mark. Are they equal? The answer is no, because 2 minus 3 is negative 1, then 3 minus 2 is positive 1. So the commutative property does not work for subtraction. It checks for what? Addition. Commutative property works for addition, but does not work for subtraction. So here is the first conclusion for two matrices. The same thing holds for two matrices. If you have two matrices A and B, we are assuming that both of them have the same dimensions, meaning that addition makes sense. A plus B is equal to B plus A, commutative property. Additive property. A plus B is equal to B plus A. So for two matrices, this property holds true. Similarly, this commutative property does not hold true for subtraction. That means A minus B is not equal to B minus A. So remember that. All right. It does not work. So that's the commutative property. Now, let me go ahead and give you another example for three numbers. Now think 2 plus 3 plus 4. Okay. 2 plus 3 plus 4 is the same as the 2 plus 3 then plus 4. So let me read it out properly for you. We are adding to 2 here, adding to 2 the sum of 3 plus 4. Okay. On the other hand, here we are adding to 4 the sum of 2 plus 3. So parentheses, remember, please excuse my dear Aunt Sally, PEMDAS. Please excuse my dear Aunt Sally. P stands for parentheses. You have to evaluate the parentheses first, right? So here you evaluate the parentheses and then add the result to this. Here you evaluate the parentheses and then add it to 4. So how you associate them, it doesn't make a difference. So both of them are the same. This is called associative property. Associative property. So for matrices, associative, as it holds for the real numbers, so does for matrices. So for matrices, associative properties are like this. A plus B plus C, three matrices you're adding, is the same as A plus B, then plus C. Now, similarly, you can quickly see that the associative property does not hold true for matrix subtraction. It only holds true for addition. For subtraction, it fails. Look, A minus B plus C obviously is not equal to A plus B minus C. Why? So look, A minus B plus C is going to be A minus B minus C. It's like distributing the negative. On the other hand, on the right, I have A plus B minus C. They are not equal. So associative property does not hold true for subtraction. So these are the two rules for addition. Your commutative property that you're familiar with, it holds true. Your associative property that you know about, it holds true for matrix addition. But for subtraction, none of these two hold true. However, for multiplication, which we have not defined, and we are going to address both of these rules later on. For multiplication, commutative property does not hold true. That means I'm just going to give you a little bit of flavor beforehand. If you have two matrices A and B, you're multiplying, they are not in general equal to B times A. That means commutative property for matrices do not hold. Okay, commutative property for matrices do not hold. However, associative property does. So that means A times B times C is the same as AB times C. Associative property for matrix multiplication holds true. Commutative property does not, but associative property does. We'll talk more about it later on, and you will get a clearer understanding of this topic, these properties. All right. So for now, remember, commutative property and associative property holds true for matrix addition. However, commutative property does not hold true for matrix multiplication, but associative property does hold true. So let's move forward and see what's next in the list of things that I want to cover. Okay. There is something called additive identity. So there is something called additive additive identity. So remember, 0 is the additive identity for real numbers. Okay, so if you take a number and you add 0 to it, it's the same number. So let's say 5 plus 0 is the same as 5, or 7 plus 0 is the same as 7. So 0 is the additive identity. In matrix, we have similar things for an m by n matrix. Okay, additive identity is going to be a matrix with all zeros that has m rows and n columns. So for a 2 by 2 matrix, additive identity is this. This is, by the way, not equal to just 0. This is 0 matrix versus 0 the number. So there's a slight distinction here. Sometimes carelessly people just write this when they mean this. Okay, this is the additive identity. For a 2 by 3 additive identity is going to be 0, 0, 0, 0, 0, 0. That means if you add this matrix, okay, to any 2 by 3 matrix, it will still be the same matrix. It won't change. Okay, this addition of zeros, it won't change. Now, while I'm on the topic, you can think of well, not only you can think of, it is the case. 1 is the multiplicative identity in the real number system. So if I give you 5 times 1, is still the 5. Or if I give you 7 times 1, still the 7. Or if I give you -7 times 1, still -7, right? So 1 is the multiplicative identity. Similarly, identity matrix that we talked about, you can kind of think of that as multiplicative identity. So like if you have a 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the multiplicative identity for all 3 by 3 matrices. Okay, so if you take any 3 by 3 matrix and you multiply it by this identity matrix, it's going to be the same matrix. It's not going to change anything. So this is the multiplicative identity for n by n matrices. Okay, so this is the multiplicative identity and this is the additive identity. Okay, any question, anybody so far about the topics that we talked about? Now, there is something called additive inverse. Additive inverse. What is an additive inverse? If I give you 5, the additive inverse of 5 is -5, because 5 plus -5 is 0. That's the additive identity. Or if I give you -6, additive inverse of that is 6, which is going to give you 0. It's a number that you add with the other number so that the end result is 0. Okay, you're adding two numbers, the end result is 0. So they are additive inverses of each other. So if you have a matrix A, then -A is the additive inverse of A. So if you add A and -A, you're going to get the 0 matrix. Let me just put the word matrix here. It's not 0, but rather 0 matrix. These are very simple concepts, yet very powerful. Additive inverse of a matrix is such a matrix, when you add these two matrices, you get the 0. So for example, I could give you 1, 1, 1, 1. Additive inverse of this is -1, -1, -1, -1. If you add these two matrices, you're going to get a new matrix 0, 0, 0, 0. Technically, it's negative here, but then I distribute it inside. So that is what additive inverses are. So let's see. Subtraction, multiplication, we have not defined yet, but I will be defining shortly. Okay. Oh, another thing. Here is another topic. Scalar multiplication. Easy. I'm starting off with the easy stuff. Scalar multiplication. What is a scalar multiplication? So let's say you have a matrix A, okay, which is m by n, and you have a real number R. Okay, so real number R is coming from the real number line. So scalar multiplication is defined as R times A, m by n. That means you are multiplying every element of matrix A by the number R. That's the scalar multiplication. R times A. So for example, 3 times 2 negative 3, 5, 0. You have a 2 by 2 matrix. You're multiplying it by the scalar 3. So that means you'll be multiplying each element in this matrix by 3. So 3 times 2 is 6. 3 times negative 3 is negative 9. 3 times 5 is 15. And 3 times 0 is 0. So that's the resultant matrix. One property of scalar multiplication is this. So let's say you have two real numbers, R and S. Okay, these are two real numbers. So R times S times A. That means you multiply S. I mean, you do the scalar multiplication by S of the matrix A, and then that's the same as RS. That means you multiply the numbers first and then multiply the matrix by that result. So this, first you multiply the matrix by S and then you take the result and multiply it by R. It's the same as multiplying the numbers themselves first and then multiplying the matrix by the resultant number. So it's pretty straightforward. There is not really any magic here. So remember, R and S are real numbers. So let me put things in perspective. So if I give you negative 3 times 2 times a matrix, 1, 1, 1, 1, for simplicity. If you evaluate it, it's going to be negative 3 times 2, 2, 2, 2. First I multiplied this by every single item, right? Then the resultant matrix is going to be negative 3 times 2 is negative 6. So negative 6, negative 6, negative 6, negative 6. On the other hand, what I do, if I take negative 3 times 2 and multiply the matrix by this resulting value, which is going to be negative 6 times 1, 1, 1, 1, is going to be negative 6, negative 6, negative 6, negative 6. And all of these are both of these are the same. So it really doesn't matter. So you can reorder the thing. So you don't have to do R and S, you could do S and R. So because real numbers, their property is that it's commutative, right? So you can do it. And associative property does seem to work here too. Few other things that I'll touch on. So let's say R is a real number, any real number. R times A plus B. A and B are two matrices, is the same as R times A plus R times B. You can distribute the real numbers. Or R and S are two real numbers. Real numbers are numbers coming from the number line. Okay, remember, real numbers are numbers that are coming from the number line. Okay, R and S are two real numbers. So R plus S times some matrix A is the same as R times A plus S times A. Okay. All right. Also, you know, R times the matrix A is kind of like the same thing as saying A times R. You can commute them, not a problem. Another topic which I kind of introduced in terms of additive identity is a null matrix. Null matrix, which is a matrix with all zeros, a square matrix with all zeros. Square matrix with all zeros. It's a square matrix with all zeros. So for simplicity, let's say n for null matrix, okay? 2 by 2 is gonna be 0, 0, 0, 0. Remember, this is the additive identity. You could have 3 by 3 or in general n by n matrix, okay? You can have n by n matrix. Any question, anyone so far? Okay. The next concept that I want to introduce is this. It's called a diagonal matrix. A diagonal matrix. What is a diagonal matrix? A matrix that has non-zero elements only along the diagonal. A diagonal matrix is a matrix that has non-zero elements only along the diagonal. So let's say, for simplicity, 2 by 2 matrix, 1, 0, 0, 2. This is a diagonal matrix because it has non-zero elements only along the diagonal. By the way, when we are talking about diagonal, we'll mostly be referring to the principal diagonal, which is starting from top left, going to the bottom right corners. Whenever we are talking about diagonal matrices, we are going to be talking about pretty much always principal diagonal, all right? Now, by the way, identity matrix is a special type of diagonal matrix too, because remember, identity matrix, it has ones only along the diagonal, everywhere else it's 0. So identity matrix is a special type of diagonal matrix with only ones along the diagonal or along the principal diagonal. So 1, 0, 0, 0, -5, 0, 0, 0, 3. That's a diagonal matrix. Some interesting properties of diagonal matrix. Okay, here are some interesting properties. Let's say D1 is a diagonal matrix and D2 is a diagonal matrix. If you add them, you will get a diagonal matrix. Okay, if you subtract them, D1 minus D2, you'll get a diagonal matrix. If you multiply them, let's say it's a square matrix, by the way. So you'll be able to multiply them. So D1 times D2 is also a diagonal matrix. So these are some interesting properties of diagonal matrices. Add, subtract, and what is it? Multiply, all of them gives you diagonal matrix. Then there is a concept that I have not defined yet. Inverse of a diagonal matrix, let's say D is a diagonal matrix. Inverse of it is also a diagonal matrix. Now, inverse of it is also a diagonal matrix. Now, what is the inverse of a matrix? So that leads to the next topic. What is the inverse of a matrix? inverse of a matrix. So let's consider a square matrix, okay? A square matrix, for simplicity, square matrix easier. Inverse of a square matrix would be, let's say you have a square matrix A, n by n, okay? Inverse of a square matrix, let's call it A inverse, is also going to be an n by n matrix, okay? All right, is such that A times A inverse is the identity matrix n by n. Sorry, not when we write this, it means that an n by n identity matrix. So inverse of a square matrix is such that A times the inverse is in, and A inverse times A is also in, or the identity matrix. Okay, so this may sound a little bit mathematical, so don't be overwhelmed. It's not that bad. Okay, so inverse of a square matrix is defined as a matrix, some matrix A. We denote it. This is not A to the power -1. It's just a notation. A with a -1 on top as a superscript that's used to indicate the inverse of some matrix A. So this matrix is, or if you wanted, you could technically call it B. Let's call it B just to say, kind of clarify things. So let's say you have two square matrices, A and B. They have this property: A times B is equal to B times A is equal to identity matrix. Then A and B are inverses of each other. So instead of writing B, what we write is just A inverse. That's just the convention or notation that everybody follows pretty much. Okay, so if you have two matrices A and B, okay, with the following property: A times B is the same as B times A, and both of them are equal to the identity matrix of size n. Okay, then it is, these two matrices are called inverses of each other: A times B and B times A. So that's the definition of inverse matrix. Again, please remember, this is an important definition. Two matrices A and B are inverses if A times B is equal to the identity matrix and B times A is equal to the identity matrix. Both have to be true, both, not one. Both have to be true. You cannot have just one, right? So instead of writing B as just another matrix, we write it as A inverse. So we say A times A inverse is the identity matrix, or A inverse times A is the identity matrix. And both of these have to be true, both true. If both of these conditions are true for two matrices, then we call these matrices inverses of each other. Okay, A inverse is the inverse of A, or the other way around. A is the A inverse of, A is the inverse of A inverse. Okay, so to put it sort of like in a more clearer way, this is the inverse of this, okay, and this is the inverse of that. So they are inverses of each other. That means they're mutually inverses of each other. One is the inverse of the other, and the other is the inverse of the one, or the first one. All right, let's see, what else do I have on my list of things? Oh, another property. These are a lot of definitions today. So I'm recording this session, so it should not be too bad. Okay. Transpose. What is the transpose of a matrix? Switch the rows and columns. Oops, I misspelled it. Switch the rows and the columns. Transpose of a matrix, you found the transpose of a matrix by switching the rows and columns. So if you have a matrix A, m by n, okay, the transpose of that matrix would be denoted by A with a little t on the top right or superscript n by m. That means this has m rows and n columns, and this one has n rows and m columns. This one has m rows and n columns. So easy way to see. For square matrices, it's easy, right? For square matrices, it's easy. The same dimension. So let me give you some example. 2, 3, 1. Okay, 1, 0, 1. That's my matrix A 2 by 3. Okay, 2 rows, 3 columns. Now A transpose is going to be a 3 by 2 matrix. Okay, 3 by 2 is going to be, you're going to be making this one, this first row is going to be made first column, 2, 3, 1. And this second row is going to be made the second column, 1, 0, 1. Okay. So that's A transpose. See, this matrix has 2 rows and 3 columns. This one has 3 rows and 2 columns. So the number of rows and columns switch. Okay. The number of rows and columns switch. Okay. Or switches, I guess. So if A is an m by n matrix, A transpose is going to be an n by m matrix. The next thing I'm going to define is the determinant of a matrix. So let's go ahead and define this. Determinant of a square matrix. By now, you know, a square matrix has the same number of rows and columns. So easiest way to define a determinant of a matrix is this. Very simple, okay? Let's say 2, 3, -1, 5. I just made it up. So let's call this A, matrix A. It's a 2 by 2 matrix, right? A is a 2 by 2 matrix, A 2 by 2. So we define, okay? Define determinant of A. That's another useful property. Determinant of A is you multiply these two principal diagonal, 5 times 2 or 2 times 5, okay? Minus you multiply the secondary diagonal, okay? 3 times -1, 3 times -1. So it's going to be 10, 5 times 2 is 10, then 3 times -1 is -3, then this is -3, then negative times negative is going to be positive. So that's going to be 13. So determinant of this matrix is 13. Let's define another matrix, a 2 by 2 matrix. We're going to start off with 2 by 2 matrix, and then we're going to expand / extend it to 3 by 3 or any arbitrary n by n matrix. Okay, so 2, -2, 1, 3, -3, 0, just to make it up. So what is the determinant of B? Determinant of B is going to be just multiply these two principal corner items and diagonal items, -2 times 0 minus, okay? then multiply these two. Remember to put parentheses after the minus, okay? This minus after that, put parentheses because this number has negative, right? -3 times 1. So -2 times 0 is just 0 minus -3 times 1 is -3 is going to give you just 3. So the determinant of a 2 by 2 matrix is defined this way. Now let me kind of generalize the concept. So if you have a matrix A, okay, A 2 by 2 with elements A1, 1, A1, 2. That means row 1, column 1 item, row 1, column 2 item. A2, 1 means row 2, column 1, A2, 2, row 2, column 2. So the determinant is defined as, so determinant of A is A1, 1, A2, 2 minus A2, 1, A1, 2. Determinant of A is A1, 1, A2, 2, which is this, right? This corner items. And then A2, 1 times A1, 2. That's the definition of determinant for a 2 by 2 matrix. Now, this may look a little bit mathematical. It's just introduction of symbols. That's about it. And I have given you a few examples, couple of examples here to actually how to calculate determinants for two matrices. Two 2 by 2 matrices. Okay, and then this concept is taken further to extend it to 3 by 3 matrices, and I'll show it to you next time, because if I give you that information today, you may get overwhelmed with all these things. Now, the next thing I'm going to talk about is a very simple concept. It's called dot product, yet very powerful. Dot product. Okay. This is the dot product. So think of two row vectors or row matrices, okay? So 1, 2, 3. And B is another row matrix, -3, 2, and maybe 0. We define, so again, we define dot product of these two matrices or two row matrices, A dotted B, okay? This is not multiplication, it's just A dot B. You have to put this dot in the middle as 1 times -3, 1 times -3 plus 2 times 2. That means multiply the corresponding elements and add the results. 2 times 2 plus 3 times 0, 3 times 0. So that is going to give you 1 times -3 is -3, 2 times 2 is 4, plus 0 is equal to 1. So the dot product of A and B is 1. The dot product of A and B is 1. Similarly, I could do other dot products. It's very easy. A is equal to -7, 0, -3, and B is equal to -2, 0, and -1. So A dotted B is going to be the sum of the product of the corresponding elements. So -7 times -2, so -7 times -2 plus 0 times 0 times 0 plus -3 times -1, -3 times -1. So what do I get? -7 times -2 is +14 plus 0 times 0 is 0 plus -3 times -1 is 3 is going to be 17. Okay, so that's the dot product. So please do make sure that you understand it. Now I'm going to formalize it a little bit. If A is A1, A2, A3, dot, 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 AN, okay, B, sorry, B is B1, B2, dot, 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 Bn, then A dotted B is going to be A1, B1 plus A2, B2 plus A3, B3 plus dot, dot, dot plus AN, Bn. So that's the general notation. And this N is the number of elements that you have in this row matrix. And similarly, you can define dot product for column matrix. Similarly, is the same thing, but instead of instead of dealing with two rows, you're going to be dealing with two columns. Dot product for column matrix. Okay, so dot product for column matrix is similar. So good, I think I have given you plenty of information. A lot of it, or all of it rather, are definitions. And even though it's a lot of information, it's easy. It's very easy to remember. It's very simple. You can go ahead and just browse through these things and you will get an understanding of it. And I have recorded this so you can watch it. And I have put a set of homework online. There are, I think, 19 problems there. I have given you enough information today in this lecture so that you can do all the problems. And it's easy. Most of these problems are multiple choice questions. All right, I think that's all for the day. Any question, anybody that I could answer? Everybody's okay? Everybody is comfortable with these things, these new concepts? Everyone okay?
Yeah.
I have a quick question.
Yes, please.
Like for the dot one, what if there's more rows and columns? Like, I don't know how to explain my question.
Oh, more rows and columns? That means instead of 3, if there are 4, is that what you mean? This has 3. So then both have to be the same. They must have the same number of columns, okay? And same number of rows. You cannot have, so you cannot have a row matrix 1, 2, 3, and another row matrix -1, -2, -3, -4. You cannot multiply these. I mean, do dot product between the two. Why? Because this has 4 columns, this has 3 columns. They have to be the same dimension. Okay, so if you have this, then both have 3 columns, right? And 1 row. So you can do the dot product. Does it answer your question or no?
Yes.
Similarly for column matrices. Okay, great.